Good afternoon. Welcome to today's colloquium. We have a very special speaker, Professor David Smith from Duke. Let me tell you a little bit about him. He's currently the William Bevan Professor of Electrical and Computer Engineering at Duke University and also the Director of the Center for Metamaterial and Integrated Plasmonics. He also holds positions of an Adjunct Associate Professor at UCSD Physics Department as well as a Visiting Professor of Physics at Imperial College. As many of you already know, he's interested in the area of metamaterials and cloaking, which is a very exciting area with a lot of applications. He's currently at Intellectual Ventures here in town. He and his colleagues at UCSD demonstrated the first left-handed or negative index material at microwave frequencies in 2000. This was postulated about 30 years before that by a Russian physicist, Veselago, and this was confirmed through their experiments. And then they followed on with a second experiment which actually reversed Snell's law. Okay, and these were both very new breakthroughs which were reported in physical review letters and Science and led to more than 2,000 citations each. So this really led to the development of this new area of metamaterials. Professor Smith has continued to study metamaterials and the fundamentals of these materials, looking at things like cloaking and transformation optics. His recent work in 2006 with Sir John Pendry and Schurig talked about an invisibility cloak. So this is obviously very exciting for many applications. And later that same year, his group at Duke University actually reported the demonstration of a transformation optic device, which looks like the invisibility cloak. This has led to a lot of publicity in newspapers such as USA Today, New York Times, Chicago Tribune, Wall Street Journal, Washington Post. He's been featured on the Today Show, in Fox News, CNN, MSNBC, and has been documented in the History Channel, Discovery Channel, and the Science Channel, and BBC. He was elected a member of the Electromagnetics Academy in 2002, and in 2005, he received the Descartes Research Prize from the European Union. He's got a list of other top honors, including the Stansel Research Award from the Pratt School of Engineering at Duke University. And I'm sure he has a lot of exciting things to share with us. So let's please join me in welcoming Professor Smith.
So I thank you all for showing up and taking time to listen to something. This sounds a little loud to me. Push this down. Sorry about that. Taking your time to learn a little bit about what we do. I'm going to talk about metamaterials and all right. I shouldn't have messed with this. I'm going to talk about metamaterials. And given the fact that usually it's a mixed audience where some people know a lot about the subject and some people don't know much about the subject, I kind of have to fit a little bit of everything in. So this is something of an introduction to the entire field and a little bit about what our interests are. And if hopefully you might think of this as a part one, and one day we'll come back and think about a part two talk to discuss all the activities that are ongoing. So I'm here as part of Duke, and we have a group at Duke that's interested in a lot of things. These are some of the things I won't be talking about, and so I'm supposed to use this pointer to point to things, so it's not the best pointer, but these are what metamaterials look like. We have a lot of interesting applications and pursuits, both at low frequency, high frequency, basically across the electromagnetic spectrum. Metamaterials aren't constrained to electromagnetics, but that's what our group focuses on. Other people look at acoustics and elastics, scattering, and all sorts of other types of wave phenomena. But we tend to like the electromagnetics and also the optics. So this is some of the surface plasmon work that I won't be talking about today. This is what our center does at Duke University, which includes my group and several other faculty that we've joined together to have an emphasis in this area that we call metamaterials. What I'm doing locally here in the Washington area is working with a company called Intellectual Ventures. And this face is probably not unfamiliar to people in this state. This is Nathan Myhrvold, who is the CEO of Intellectual Ventures and was a former CTO of Microsoft. He's also, as you can see, a chef, an accomplished chef with a nice set of cookbooks to his name. Why I'm here is a lot to do with him because Nathan Myhrvold thought that metamaterials was an interesting subject, kind of weird, kind of quirky back in 2003, 2002. and really decided that intellectual ventures should take a stake in this emerging area before any of us knew, one, if it was even right, or two, what it would be good for, even if it were right. So all of this development, they've been in this field now for years, basically since 2005. And just recently, we decided that things were getting mature enough for a number of reasons to actually start a more focused commercialization center. And so that is what we're doing at the IV Labs. We plan approximately 8 employees over the next year, but it could be more because things are moving pretty quickly. The difference at the IV Lab that we're trying to fill is a more focused, market-driven type of research, looking for a match between real-world applications and metamaterials. It's a little bit different what our group does at Duke, maybe what many other academic groups do, but it seemed to be the time to have that happen. And really, there was no, it's hard to imagine another place like intellectual ventures where something like this could happen. So I'm also representing that opportunity here. So I'm starting with the punchline before going into all the details. The punchline is that it's already been a successful process in that intellectual ventures spun off this company called Kymeta, which is just up the road in Redmond, that was actually founded by Nathan Kuntz, who I guess was here just 5 years ago, talking about the potential of metamaterials. And this was one area, after a little bit of focused market study, they decided to take the metamaterials concept and really boil it down to addressing one particular market need. And the market need that they looked at was satellite technology. And what they found is that satellite terminals really are based on 1940s technology, and we're just dying for some new innovation. They're usually based on fixed dishes that rotate, tend to be expensive, tend to have high maintenance costs, or the alternative would be a phased array, which is expensive and has other issues. So the Kymeta technology, or the idea of using metamaterials that Intellectual Ventures developed, was to address this market with something called MSAT, which is a metamaterial panel antenna. And I won't have time to go into the details of this. It's yet another whole talk. But it's just the point that metamaterials have matured to the degree that you can actually look at coupling what we've been working on for years, which was very, very fundamental when we started and still is in some ways, to something very commercial and very product-oriented. So just as again, part of the punchline, Kymeta emerged on the list of 50 most disruptive companies from MIT Technology Review. Kymeta has been around since August 2012, and it's on this list with companies like Google and Microsoft and Amazon. So that was pretty exciting, actually. So that's the introduction as to why this might be interesting to you, and then I want to take a step back now and really talk about where it all began and what it's about. So again, when I kind of started working on this before this term metamaterial even existed, just as an interesting pursuit. And this was the basic idea behind it. What is a metamaterial? Often people associate metamaterial with a thing, but actually for us it's really been a design approach, more conceptual than a thing. It leads to things, and those things often look like this, and I'll explain what those things are. But for me anyway, it's really been more about a conceptual design approach to arriving at electromagnetic structures that might be difficult otherwise to arrive at if you were to pursue just a pure engineering approach. The language of engineering is typically in things like impedances and say, transmission line theory. The language of metamaterials really is the language of materials, or materials physics. And certain solutions, especially when you're talking about wave propagation, tend to pop out more naturally in a materials description. Both are equivalent in the end. It's just Maxwell's equations, but there is some advantage sometimes in using a materials approach, especially when we talk about things like transformation optics. So when you think about metamaterials, you think, what are they good for? That was a big argument that we had for a long time. And so I've just pulled some stuff from the internet that I found. Any place where a material enters your design is potentially a place where a metamaterial can enter the design. And so I just pulled off a bunch of antennas where you can immediately see visually where the material enters, whether it's a shape beam antenna like this dielectric lens antenna, or the substrate for a patch antenna, loading of a horn, radome materials. All these things actually use materials, and in a very simple way, without thinking too hard, you can think about introducing metamaterials for applications like these. Again, we work across the spectrum, but if you think about communication systems more broadly in metamaterials and think where are the entry points, there's a bunch of elements in a communication system, and in many places you can think of where you might introduce artificially structured materials. Again, I haven't told you exactly what they are, but I'll come to that. And this is some of the spots. Most antenna systems, or a lot of antenna systems, will have something like a lens. You might actually be able to improve the antenna element. There may be a feed network that involves things like transmission lines. And then down on the baseband level, in the analog system, there might be components that you can bring in metamaterial ideas. All of these things have been looked at. Again, I can't go through all of them, but all of these things have a place, and it's just a matter to find out which one of the metamaterials concepts could potentially displace existing technology also, which is very good, and engineering's been around for a long time, so what you engineer certainly has to be better and cheaper and all the other things that you want. What are the fundamental limits? At least for antennas and more broadly apertures, we usually go on the record in saying you can't beat these limits. There's been a lot of confusion about this in the field, which hasn't been great, I think. Particularly small antennas is a big interest from various funding organizations. Small antennas are limited. If you shrink an antenna, its properties become independent of any material or any aspect of the antenna. They're really set by causality at the most fundamental level. So there's something called the Chew limit, which tells you the trade-off of the size, bandwidth, directivity, all those sorts of things that you might be interested in. And there's no way with a passive metamaterial to beat this Chew limit, and that at least in my opinion. And also there's aperture limits that tell you for a given aperture size, and we'll come back to this in a little bit, what is the best directivity you can get or the best resolution. Again, you can't beat that. There's other things in the area of compressive sensing and what's called super resolution, but that's a little bit of a different thing. That says you can undersample a scene and get diffraction limited information. But yeah, at the fundamental electromagnetics level or optics level, you can't beat these aperture limitations. So that's what metamaterials can't do. So these are the things that if they come up immediately, I'd say no, metamaterials are not the direction to go there. But there's lots of other things. So now I want to take a step back and try to tell you what these things are, where they came from, how I got into this field, and hopefully do that quickly. It starts with what a material is. I won't dwell on this just in the interest of time, but basically you know that a material is composed of a bunch of atoms, and you don't think about those atoms because they're on a scale that you don't care about. You care about the material, and so you sort of lump all the interactions of these atoms into something that is more manageable to deal with in terms of getting you the engineering or the physics that you want without having to worry about doing a quantum mechanic calculation every single time that you want to understand the material. So there's a couple scales that you have to worry about. There's a molecular scale, which I'll call delta there, and a scale of inhomogeneity, which I'll call D, and then lambda might be your scale of physical phenomena. And the point is that we should be able to neglect delta, and we do that all the time. We know that what these molecules really respond like are they're so small that usually you can think of them as dipoles, and you can think of them as either electric or magnetic dipoles. Electric dipoles can be thought of as a charge separation or a current sloshing back and forth, up and down. And the essence of magnetism is currents flowing in a loop, whether it's spin or an actual current. You have to think of some sort of rotation, but that's the two flavors of response of a material, and they're caused by these dipoles. You can imagine that these dipoles sit in a host where they have lots of other like dipoles, And you can define a polarization and a magnetization just based on averaging over all these point dipoles. And in the end, you have to do this carefully. You have to take into account all the interactions, but that's all known. In the end, you can take all that complexity and you can dump it into a material. So you imagine that we replace that process of thinking about all these discrete objects, and we replace it with something like a continuous material. And we describe that continuous material with the parameters epsilon and mu. That's a lot of simplicity. That's a lot of cutting through the complexity of material physics and interactions and actual point scatters into something that's very simple and can fold right into Maxwell's equations, just like that. So Maxwell's equations in media have these other parameters that show up, epsilon and mu, and all the complexity of the material is condensed into those parameters. You just have to know those functions, and oftentimes you can do very approximate functions, sometimes even constants, to tell you how a material will impact your wave propagation. So after that, the question is just solving Maxwell's equations, and I'll focus on, in what I do throughout, on my pointer's not showing up. It doesn't show up on the screen. Sorry about that. I'll just have to point. So the TM modes reduces to a fairly simple wave equation. You just have an EZ component, or the magnetic field is transverse to the z-axis, and I'll tell you what the z-axis is later, but you get a couple simpler equations to work with. But these are all Maxwell's equations, and these are the wave equations. This is the anatomy of an electromagnetic wave. It's got an electric field, a magnetic field, and that's why you need both electric and magnetic response in order to really control it perfectly. Usually materials, at least at optics, just you think of as having electric response, but you're leaving out half the story if you do that, and you don't have complete control, for example, over impedance. So there's a lot of ways around that, but for example, if you wanted to create a matched surface, you might think of matching epsilon and mu. You can't do that if you only have epsilon. So to truly manage electromagnetic waves, you want to usually control both epsilon and mu. And this is the anatomy of the wave. This is what it might look like if it's really a three-dimensional object. But if you look at it from the side, it kind of looks one-dimensional. If you look at it from the top, this is a plane wave. You can see that you get these bands showing the crests and valleys of the wave. And I like that view because we can actually do that experimentally, and also simulation-wise, we consider this a quasi-two-dimensional structure. So the next question you might ask is, what sorts of materials exist and what can you make? And these are parameters that once you have the epsilon and mu, you get these familiar parameters like the index of refraction, the wavelength in the material, which is shortened by epsilon and mu, and the wave impedance. A wave propagates like what I've shown down there. And you can ask what really is available. And I'm going to make what I'm going to call a Vesilago diagram, where I'm going to put the real part of epsilon and mu on an axis like this, and quantify or describe materials based on that axis. So in the upper right quadrant, that's where most materials are. Epsilon and mu are greater than 0, and those would typically be transparent materials. Metals have an epsilon that's negative at optics. I'm thinking of optics. They're really imaginary if you think at low frequencies, so I'm not talking about conductors exactly. I'm talking about at optics where epsilon is negative. You have opacity, so things are opaque there. Ferrites, magnetic materials, often can have a mu that's negative, and if epsilon is positive in the fourth quadrant there, you have, again, opacity, and that can be done with ferrites. And then there's this area here, in the third quadrant, where epsilon and mu are both less than 0. Again, just if you multiply them together, you get a positive number, so the square root of is positive, so the index should be positive there, and so you'd expect them to be transparent. And this is actually where metamaterials started, because this is a region that was completely unexplored up until basically the metamaterials concept was introduced. So before I come back to that, this is now what metamaterials are. They're designer dipoles. So I've talked about atoms and molecules can be described as dipoles. As far as Maxwell's equations are concerned, they don't know anything about atoms and molecules. All they know is dipoles and dipolar response. So if you create some sort of element, that element doesn't have to be microscopic, it just has to be smaller than the wavelength. That works perfectly well to form the basis of an artificial atom to construct a material. This is not a new idea. It's been around for quite a while, since at least the 40s, 30s, probably even before that. But in recent times, it's come back into vogue because of the ability to, the realization that you can really address unusual material properties and our ability to actually design quantitatively and precisely various materials using this approach. So if you want an electric element, you might do something like this I-beam, which gives you a charge separation if you apply a field, electric field. And if you want something like a magnetic response, you might use a split ring resonator, which is on the right, which if you imagine just inductively driving it with a AC magnetic field, you'll form currents that run around in a loop, and that give you a magnetic response. So those are our building blocks. And we can take these, put them into a medium. At the unit cell level, it's a nice connection between electrical engineering because they don't have to be metals and they don't have to be circuits, but they're convenient to think about. And so you can do your electrical engineering at the element level, writing things down as electrical circuits, if you like. You get the properties. This one on the left is non-resonant, or we call it non-resonant. These other two are resonant. And if you like that description, great. You can turn that into an effective medium property. And so you can quickly jump to the material description, which gives you an epsilon or a mu description of that same structure if you imagine putting it into a medium. And so, for example, here you have what becomes really a nearly dispersionless epsilon. It's just basically a polarizable substance. The split rings give you a mu that's described by that resonant form. This is approximate. And those ELCs, we call them electric resonators, give you an epsilon that's resonant. And the point is that when you combine these things, you really have access to all ranges of material properties, whether mu you want greater than 0, you want it large, you want it negative, you want epsilon large, positive, negative, near 0, between 0 and 1. Anything you want, you can get. And these curves can be tuned anywhere just by changing the geometry. So now you've got the building blocks to really make any kind of material, positive, negative, whatever, and you're not constrained anymore by what nature just happens to provide you with, which is only a limited subset of these things. So back to the story about the Veselago chart. Veselago looked at this chart and said, why are there no materials with epsilon mu less than 0? And in this paper, which really was sort of a unique paper published in 1968, he wrote a paper called The Electrodynamics of Substances with Simultaneously Negative Values of Epsilon and Mu. And this is a picture of him sometime around, I think, 2004, 2003. And he analyzed what would happen if epsilon and mu were both negative. And he found some interesting results that, for example, the direction of energy flow and the direction of phase advance were anti-parallel. And that leads to a lot of interesting physics, including the reversal of Snell's law, Doppler shift, Cherenkov radiation, all these interesting physics effects. I'm just going to focus on one, that the index is negative. So the index is the square root of epsilon times mu. It's clear that if epsilon and mu are both positive, that the square root is just a positive number. But if they're both negative, you might think negative times the negative is positive. I take the square root, great, it's transparent. But you have to remember that the square root of a number can be either plus or minus. And it turns out that if epsilon and mu are both negative, then the correct sign for the index is negative. So you get a negative refractive index if both epsilon and mu are negative. Veselago had a lot of interesting reasons or conjectures as to why such materials didn't exist, but in the end, they don't exist. So this is a diagram, a refraction diagram on the top is a conventional diagram, and on the bottom is a diagram showing negative index. So a wave comes in, refracts actually to the opposite side of the normal, so that gives you negative refraction. And if you look, we've drawn this diagram carefully, you see the phase is coming back towards the interface, which is fine because energy has to be flowing away from the interface. And if you drop this into a simulator like HFSS or CST or any of the common ones, that's exactly what you get. Again, my pointer just not going to point, I think. You can really predict some interesting physics based on negative index materials. So, like I said, now we have a recipe for actually making these things. Just a combination of a split ring resonator and a wire, carefully done, should give us this recipe of negative index. And these were some of the early structures. The one in the upper left there is one that we first did in 2000, later one in 2001 to the right. The one in the lower left was a later one, 2003, done by Boeing. And then there's been various incarnations of these negative index materials throughout the years. So I wanted to talk about 2D measurements. This is the type of structure. It's easy to confine electromagnetic waves in 2D by a couple of metal plates. And so that's what this structure is here, what we did in the early days. And if you put an antenna in one of the plates, you can actually sense waves that are injected either by a feed like that or through the center somehow. So later on, we have a similar setup. That's, again, this is with the chamber open, but if you close the chamber, the bottom plate is on a stepper motor, so you can actually leave an antenna in the top plate, move the bottom plate around, and actually build up a picture of what the field is doing experimentally. So here's a picture of just that. This is a simulation of a wave coming in to a wedge. So this is a Snell's law experiment. And on the left, you're seeing what is predicted for the refraction. And on the right is an actual measurement taken in that chamber. This is done at microwave frequencies. The wavelength is just a few centimeters. And you can see that aside from some sort of turbulent jumping around, you actually get what you expect, that the wave is coming out to the right. So the experiment was done with something like polycarbonate or just some piece of plastic that has an index different from vacuum. We map the fields, and I'm basically animating the phase. Nothing clever here. So this was done with a vector network analyzer. So now if you do this with a negative index material, the first thing you say is, where am I going to get that? We know we can make it using split rings and wires, but if you're a skeptic, you say, will it really do what you will really behave like a negative index wedge? So this is another experiment that was done with a metamaterial wedge. You can see on the lower right, and the elements are shown there on the upper right. So this is a simulation of this hypothetical material on the left, and you can see that it's actually behaving like Veselago's prediction because the phase fronts are traveling backwards even though the energy is traveling forwards. Now if you look at the experiment, that's exactly what happens, and that was actually pretty exciting. Waves are coming in inside the material, and it's not a material, it's this construct that's made like that. You actually see that full wave fronts are being formed, and they're traveling backwards, and then at the end they are actually refracting negatively out of the wedge. So again, this is a pretty good demonstration of the power of the artificial material concept. So that led to a lot of controversy, actually. You might think it was all settled by those early experiments, but it wasn't. There was tons of controversy that happened just immediately after that. I won't go through it all, but you can sort of see the various like problem of left-handed materials. They were called left-handed materials back then. Is there an experimental verification of a negative index of refraction yet? I actually reviewed this paper, and the original title of this was, is there an experimental verification of a negative index of refraction yet? No. So through the review process, I got at least the no out. And more like this. One of the most interesting ones was this one that said wave refraction in negative index media, always positive and very inhomogeneous. And these authors actually went and created a website that is still up today. This is from Roger Walzer's website that went through and said this can't exist for a lot of reasons. Didn't like anything about this, either the method of realizing it, the possibility of negative index, everything. It's hard to describe why they didn't like it, but this animation from their website shows that they believed that the phase fronts would have to exceed the speed of light Anyway, it was a long controversy. It went for a couple of years. In the end, there was a lot of press about it, and you can see that negative reaction to negative refraction, things like that. But in the end, the result was put to rest by a couple of experiments, which I'll show briefly. And in fact, Seattle played an important role, or at least Tukwila, because the experiments that won everyone over were done by Boeing. And this is the work that was done by Boeing. If you looked at our little structure, it didn't look so professional. DARPA came in on a program that we were on with Boeing. They did this a little bit better. Instead of using the confined waves, they did free space. They actually made something that looks like a Snell's law sample. They did it with a big setup. They were sure they were in the far field, all these sorts of things. So these are negative index wedges that are nice and shrink wrapped so that all the metamaterial elements are inside. They look just from the surface like the Teflon wedges. And here is their results, which were extremely good, showing both a Teflon wedge and the negative index wedge are shown. The negative index wedge is dispersive, so you see it only works over a limited range of frequencies, whereas the Teflon works over every frequency. But if you look at the theory versus experiment on the lower right, you see that really the negative index is shown, and it's exactly what was expected. So these were experiments that were hard to refute and kind of drove the field along. So they convinced almost everyone. This book came out in 2009, and it's still controversial. And this book was important because it was written by Ben Monk, who was a very, very well-respected engineer. And if you look closely, I don't know if you'll be able to see it. Well, I'll just read those words. He denies the existence of negative refraction and provides convincing alternative explanations. So even still, by 2009, we thought we'd settle everything. It's still not quite settled, at least for some people. But if you look closely at the cover of his book, there's a nice statement there. So you see that he's showing a refraction diagram, and he's showing positive refraction, which is the red, and negative refraction is the blue. And if you look closely, you can see this is the cover of his book. It says no. So he definitely did not like negative refraction. Fortunately, other people do, and this concept is actually out there, and I thought this was kind of funny. Someone sent it to me. This is a clip from the Big Bang theory, and if you look in the background, you can see Vesilago's diagram, actually. So things like this pop up. That's kind of interesting. So it really crossed over into a mainstream concept. So our group does a lot of metamaterials, and we needed a set of techniques that allow us to get what we want in a way that's reliable and reproducible. So I won't go into the details, but we can do this either theoretically or simulation-wise or experimentally. You can scatter a wave off some collection of objects and do an S-parameters retrieval, assume it's a continuous material, and really ascribe to it things like index, epsilon, mu, and that works pretty well. And there's a variety of methods, and this is now an area of research. But the basic idea is shown up in the upper right, that even though you have a collection of discrete objects, your waves really see what looks like a continuous material over to the left. And we've got ways of working out and forward designing what these properties are. So I've talked about interesting materials. Negative index materials are really fascinating. They found very little application for a variety of reasons. There's other types of things you can look at. One of them is gradient materials, and gradient materials are actually a really good match for metamaterials because you can engineer really precisely controlled gradients just by changing some aspect of the geometry. So in the top, I've made a gradient magnetic material just done by changing that little capacitive gap. That changes the resonant frequency, so at any frequency, you actually can implement a gradient in mu. Likewise, if you want to introduce a gradient in epsilon, you could just take something like these I-beams and change their length, and that gives you a gradient. So you can get interesting materials. You can control things like the isotropy or anisotropy, so you can create interesting anisotropic materials with both electric and magnetic gradients. And that's a lot of degrees of freedom. gradient optics are known. They've been around. You don't see so many gradient index lenses, at least at optics, because it's difficult to get very large gradients using typical dye diffusion methods. Artificial materials definitely can address that and give you much larger index contrast to make more useful structures. There's a variety of ways of doing that. Metamaterials give you a little bit of an edge there. So we're moving from refractive optics, where you might think of the interface as having all the control. You're really relying on Snell's law, to gradient optics, where you're starting to rely on Fermat's principle and the volume of the material. So trading off a simple material and complex surface engineering to a simple surface and more complex volumetric engineering. So a simple example of that is if you make a linear gradient, you can steer a beam. This is what we've done here. This is a metamaterial just with a gradient and a couple impedance match layers. And this is the experimental data. You can see it just perfectly bends a beam. This happens to be broadband and everything else that you'd like, low insertion loss. And again, we're getting an index gradient that goes from here from around 1 to 1.5 or 1.6, which is a pretty large gradient if you were thinking by optical standards. And again, you can make something like a lens, and that lens has such low insertion loss and such good properties that you start to think this might actually be useful for something. So just as an example of where taking this from the fundamental ideas to something more practical, we did a project with Toyota to look at automotive radar. And this is a system that we looked at which has a big lens, a big refractive lens sitting in it. And this is a 77 gigahertz system. So just to be, at least in the ballpark, we decided to make a gradient index lens and see if we could have better performance than that lens that's sitting inside the Bosch system there. That's an older system. And that's what was done. I won't go into the details of all the fabrication, but after playing around and coming up with the design and putting everything together, we ended up with the lens that you see in the pictures here. And the lens was designed to have the exact same characteristics as this dielectric lens that was sitting in this Bosch system. And you can see that the profile is much, much smaller, probably lighter weight, actually quite a bit lighter weight, and you can just see the savings there. So there is actually potentially some advantage in even a simple mundane application of metamaterials like this. You don't see these gradient index metamaterial lenses yet in your Lexus because that dielectric lens is probably about 20 cents to manufacture. And right now, at least, the metamaterial lens is not 20 cents to manufacture. So there's been a lot of press to push things to higher frequencies. We're interested, again, across the spectrum, but things that are a little bit more likely to lead to application. So there's been some hero experiments, and I won't go into all those, especially some from Berkeley and other places doing things that even toward the visible. Those tend to not be useful. A lot of what you see is not terribly useful, but there are potential useful directions. And so we decided to look at diffractive optics, taking what you've seen there and using that to make a diffractive optic, which has the advantage that it can be very thin. The losses that you often get in metamaterials, because they're metals, which get lossier as you go up to higher frequencies, especially towards the visible, can be mitigated because you need very thin samples. So we decided to take a stab at IR optics. And sorry for this busy slide, but the essence of a diffractive optic is that there's a Fourier relationship between what you want in the far field and what you want in your aperture plane. So if you want any particular distribution in the far field, you want to create its Fourier transform. This is a rough way of saying it in the aperture plane, which means you want control over your aperture. So the more control you get over your aperture, the more types of optics you can make. And again, these can be relatively thin and high efficiency. So this is well known. This is Fourier optics. Simplest example of that would be a diffraction grating. And it's useful to show the concept here because I'm going to take a simple diffraction grating, which typically has many orders, some of which radiate. And so I'm showing here a diffraction grating, which is a periodic set of slits. And it leads to a few beams that you might expect in that interference pattern that you see there. So what if you want to get all your energy into just one diffractive order? Then you've got to do something different. And that difference is what's called making a blaze grating. So this is a very simple example of a diffractive optic. So there's a couple ways of doing this. One way is to make little ridges in some dielectric. But another way would be to create a gradient index grating, which is shown on the last piece there. So if you make a gradient index grating, you can actually reduce all the other diffraction order coefficients to 0 when you hit the right thickness or phase shift and put all your energy into one beam. This, again, is just an example of what you could do, and we want to do more sophisticated things, but just as a first getting in the door. So we wanted to make something that would put all the energy into, say, the +1 order. We decided to make a structure that has the parameters shown there. We used 10.6 microns because it's easy to get a laser there. This has got to be done with nanofabrication or microfabrication. This was done with a collaborator at Duke, Nan Jokerst, her group. It was done by putting using gold in SiO2 and doing a multi-layer stack. We decided we needed 6 layers, or between 6 and 8 layers, and you can see the orders. As you increase the number of layers, by the time you've got 6 there, you have everything into the +1 diffracted order. So what we're doing, the idea is to make a linear chirped grating. So it goes from an index to a larger index and then repeats with a repeat distance of 60 microns. That's what we're trying to make. And again, we have this technique where we can retrieve the properties of various elements, and we call these unit cells sometimes, but they're elements that we're just changing, and we can get, by changing the length, we can get a refractive index, in this case, that we were able to vary between 2 and 5.5. And we can put that, extrapolate to get a linear gradient and linear sawtooth structure. So this is a structure that was made. I won't go into the details of the fabrication, which turned out to be a little bit more tricky than we anticipated. But in the end, we were able to make this structure, and you can see on the right, you can see that banding. That's these little elements going up to increase the effective index and then restarting. So that's a grating, and you can see it if you're looking close at the intersection between the high index region, which is these larger I-beams, and the low index region, which is like these little dots. So we can get 61 independent phase levels from this to make our gradient index, which is actually quite a lot. That's more than what you have in typical blaze grating optics. So this is the experiment that was done. We got to, I think, 4 layers, and then the thing broke. So we couldn't go all the way, but we got great agreement with simulation and theory that we're putting more of the energy into the +1. And this allowed us to come back and say we were getting a delta N of 3, which is huge at IR frequencies, again, enabled by this metamaterial structure. So we can now take this and go one step further and make a phase hologram, a metamaterial hologram. And so for evident reasons, we chose this as the object. The Fourier transform of this is this mess that you see on the right. But this is just making a computer hologram, except now we're going to make this with metamaterials. So that's something that was done. Same technique. And this is what we expected to see. This is a sample that was fabricated. That's the actual SEM picture of the sample. Different views. We broke things up into cells, and you can see just the various scales of magnification there, what the structure looked like. And this is the experiment that was done. You can see light comes in, goes through a polarizer, hits the hologram, and then we just measure with the camera. And this is the hologram that was actually measured. Made a mistake in the design between Fresnel and Fraunhofer. It's a long story, but the result was that we lost the E in this particular design, but we got most of Duke, so hopefully that was okay. More recently, we asked, what is the advantage here for metamaterials? there's not much in making a straightforward hologram because that can easily be done. But if you start thinking about exercising the anisotropy, you could do something like this, which is a dual polarization hologram made by using elements where you're changing things. You've got like crosses, but you can change 2 degrees of freedom for the 2 polarizations. And so you can actually make, in this case, 2 different gratings on the same sample. And as a function of polarization, you can get 2 different directed beams, which is shown here. And you get extremely good polarization extinction in this case. And again, you can make a polarization hologram, except now a dual polarization hologram. This time we understood the difference between Fresnel and Fraunhofer. And you can see that these 2 images require these 2 different phase holograms shown on the right there. And that can be done by adjusting these 2 degrees of freedoms in these little crosses. And if you do that, this is the result. This is the actual measured hologram. I'm changing the polarization now from 0 to 90. And you can see that we go from the Duke to the Blue Devil. And in case anyone doesn't know, the Blue Devil is the mascot for Duke. That's why we did that. So that worked. You take that degree of complexity, a diffractive optic is a well-known thing, even if we have some advantages with metamaterials, but we have more because we haven't even exercised the magnetic response or really done a lot with full 3D anisotropy. So when you have that much degree of freedom, the question is, what can you do with it? And that's what led to this idea of transformation optics, because we needed a tool to harness all the flexibility that we had with these possible gradients in all different directions and electric and magnetic. So the idea behind transformation optics is actually really simple, conceptually simple. It relies on what's known as the invariance of Maxwell's equations under coordinate transformations. So you can do a coordinate transformation, and light sticks to the metric of the space that it thinks it's in. So if you transform the coordinate system, you're going to transform, just imagine writing down a bunch of rays and then transforming that. All the rays are going to transform. Okay, that's a good conceptual thing, but it turns out if you make use of the invariance of Maxwell's equations, you can immediately come up with a specification for a distribution of epsilon and mu that will cause light to do exactly what your transformation said it should do. So again, the traditional way of controlling light is a simple material, engineer the interfaces, but now you've got this other method, which could be perform a coordinate transformation, and then use that to specify a material that will give you that transformation. Conceptually, it's really a nice thing to do. It just leads to very complex materials, and if you didn't have metamaterials, you would have said, okay, that's a cool little thing, but I'm not going to go any further with that. But now with metamaterials, you can actually think about going further and making these things. And what I've shown here is just this concept down at the bottom of visualizing a coordinate transform. So when we were thinking of what to do with this, all of this degree of freedom, John Pendry suggested as a joke we could make an invisibility cloak. And he's the one that developed this idea of the transformation optics when we were working together. And that seems, for us, that was a fun concept. We didn't really take it too seriously, and he didn't take it seriously at all. He just, he's a theorist, so he wrote down and said you could do this, and he was thinking actually Harry Potter. But we took it seriously, and when you think about what invisibility means, there's enough examples in the popular media to be inspired by. The one I found most inspiring was the one at the bottom there, the bottom center, which is Predator, which I always thought was a reasonably potential depiction of invisibility. There's a couple ways of doing it. You might think of the Invisible Man up in the upper left, and Kevin Bacon there in the modern Hollow Man, Invisible Man story. Would be like if you took some sort of chemical and it did something to your actual atoms to make them transparent, which is not very likely because they'd probably stop working other ways. But some of the other depictions, for example, Star Trek has a very good set of episodes, and they've actually thought this through as to how their invisibility cloak works. May not be feasible, but it's not entirely crazy. And then the Predator, which is never explained, has some aspects to it that we found inspiring at the time. So what do you have to do to make something invisible? You want to make light look like it has passed through empty space. When you put an object in space, light actually reflects from that, and that's how we detect it. If it's translucent or semi-transparent, you can still detect it because it has a refractive index that's still different from that of vacuum, and that's, for example, why we see Kevin Bacon over there, because presumably he's not entirely invisible, or he's got some mismatch, and so you can still detect it. And also you can detect it from the shadow if you're standing on the other side of the object. Light coming through, which gets deflected away, doesn't reach your eye, so again, it casts a shadow. So the picture that you start to form, what you'd like light to do, is what's shown in the fourth point there, which is to route around your object. And that's the idea that metamaterials can potentially play a role in. If that's space, that's not so easy to do. But if you imagine extending that and putting something that might be a cloak outside of that, that is possible to do. And the design to do it is very simple. It's a transformation that just looks like this. It pokes a hole in space and pushes that space outwards, and that's what gives you that exact type of behavior of these rays kind of going around. Remember, light's going to stick to those lines because that's its metric. It's just been displaced by this coordinate transformation. And now we're going to use what is a transformation optics recipe to actually make a material that will do that coordinate transformation. And I won't go through the details of how you arrive at that, just to say it's not that hard to actually use these in practice and come up with the material design that gives us that exact cloak. So these are the material parameters that are required. In the center column there, full parameters means that's exactly what you'd want to make light do exactly that routing trick. You need to control both two components of mu and one component of epsilon for one polarization of light. If, however, you are a little bit on the cheap and you can't do the full material, or you're in a rush like we were, you can actually get away with just controlling the rays by only controlling one component of mu, and that's what we decided to do back in 2006 to kind of really demonstrate what could be done with the transformation optics. And so this is the difference between the idealized cloak on the top and the approximate cloak on the bottom, which does have a shadow and it does have reflection, but it's at least showing the signature of cloaking with the rays kind of getting pushed around and then reformed on the other side. And you can see right away that the really tricky part in this lower case is just getting the radial component of mu to go from 0 to 0.25. That's it. That's what we had to do. So this is a picture of what we made. Again, this is a metamaterials trick. These are the actual elements that were used, one for each circumference. And this design, which was made by Dave Schurig, had the property that it really took mu r from 0 to 0.25 or thereabouts. And this is showing in one image the coordinate transformation and the metamaterial realization of the material picture. Both should be equivalent as far as electromagnetic waves are concerned. And the experiment that was done was, again, a mapping experiment. And right at the frequency where it was supposed to operate, that's the comparison we got with the simulation above, actual measurement below, and really they looked perfect, only at the design frequency. Later on, we went back and actually measured the cross-section. Well, I'll come back to that, but this I like to show this picture because Dave Schurig is in the upper right in his third interview with Fox News, and I like the picture because he decided it was a good idea to wear sunglasses for that interview. I don't know why. It's a long story. But anyway, we went back and we measured the cross-section, and we didn't even really expect it to work this well, but you can see that the cross-section is pretty high, and comparing on the upper right, The blue line is just a conducting cylinder, and then the red line is conducting cylinder plus cloak. And you can see at the design frequency, the thing plummets down and actually has a lower cross-section for cloak plus cylinder than just the cylinder, which is kind of amazing for this rough design. So we actually reduced the scattering cross-section isotropically from the structure by 24% at the design frequency. Since then, more recently, we've made a full parameter cloak, and it really operated perfectly. I won't show a picture of that, but that was done just last year. So I think I'll just say a couple more things, that transformation optics has so many degrees of freedom, and there's so many people now looking at this. A lot of good ideas have come up. About the same time, there was this idea of what's called conformal optical mapping that was introduced by Ulf Lenhart. If you look at the grid pattern that you see for these two types of transformations, you might imagine these are two cloaks. It's hard to see probably, but the transformation optics cloak has grid elements that are not square. They're kind of skewed. And if you look at this conformal cloak, you see things that look more square. And that coordinate transformation is telling you something about the material. And immediately, the more skewed and more irregular your elements are, the more anisotropic your material has to be. This conformal cloak can be purely isotropic. It can be purely dielectric, in fact. So this is really advantageous, but it doesn't work so well. The transformation optics works perfectly, but it's hard to get the material. So there's been an intermediate development of what's called quasi-conformal, where you kind of get a little bit the best of both worlds. It's hard to describe, but it came out in this paper by Jensen Lee and John Pendry in this format where they were looking at hiding an object on a ground plane. So you do a transformation, you create a bump in this ground plane, the bump scatters, but now you can put a cloak on top of that bump, and it restores the beam, which you see in the second panel there. And the point is that it's a sort of a constrained artificial geometry, but that cloak can be broadband, and it can be low loss, and it can scale up towards optical. So it has a little bit more potential application. Here's, again, showing the same sort of thing. If you do just a generic transformation optics transformation and then throw out the anisotropy and just try to make it a dielectric cloak, it doesn't work. It's no better than having no material. But if you do the quasi-conformal transformation, which is a little bit of optimization, you can get rid of the anisotropy, you can ignore it, and you end up with a very good cloak. And that's shown in the lower right there. And this is something we demonstrated in 2009. And since then, I don't have the slides, but this has been demonstrated up through optical. So it really did work in various incarnations. So again, thinking from the practical point of view, this was some work that we did with Nathan Kuntz when he was a grad student at Duke. We decided to look at something like a Luneburg lens, which is a fantastic imaging device. Its only downfall is that it's a sphere. It's spherically symmetric, so rays come in, focus perfectly to the surface of the sphere, not the greatest match for planar detectors. So the idea here was, could we do a coordinate transformation and flatten a Luneburg and come up with a material specification for that? And as it turns out, it's a very simple transformation. You can just collapse this. You can use quasi-conformal. And you can see by the ray trace diagrams a Luneburg and a flattened Luneburg. And you can see now that we're actually able to focus all the rays perfectly to a point on the back of this detector. And it's a planar detector now, or could be a planar detector. And Luneburgs are nice because they have no aberrations of any order and any geometrical aberrations. So again, this was done as an experiment. Very simple elements, these I-beams made into this complicated gradient profile. But it worked, and these are the experiments shown on the right. And compared with ray tracing on the bottom, you can see that you're really getting very extreme focusing. Obviously, true Luneburgs have have an infinite field of view. If you flatten it, you reduce it some, but you can still get nearly 90-degree focusing. You can take this concept to things like Maxwell lenses, and you can make a perfect relay lens by flattening two sides of a Maxwell lens. A Maxwell lens is a gradient optic that takes points on one side of the lens and images them perfectly to the other side. And again, that can be done very simply through a coordinate transformation, and that's what you see there. So all of these types of structures are showing you the science behind metamaterials and where things could go. They transition pretty well up to IR and possibly even optical, and might have actual uses. Just to close out, we've been talking, and what we've been inspired by has been a lot about bulk or volumetric metamaterials, but there's also guided wave versions using complementary, where you just use a Babinet equivalent, and those are guided wave structures which are often more conducive to engineering applications. So again, I won't go through the details, but I just leave you with one example that's a little bit more engineering oriented. There's these things called Luneburg lenses, Rotman lenses that are often used, and they involve a quasi-optic region. So you bring in a feed, it is focused through this quasi-optic guided wave region, and then goes out to antennas. So each feed gives you a directed beam on the output. And their size is really set by geometrical optics, really. So the idea was, could we take a transformation and actually reduce the profile of something like this? This is a circuit board-based Rotman that was made up. And here's a very simple transformation. We're just going to shrink space in one direction, like this. The transformation requires you to have a gradient magnetic material. That magnetic material, as it turns out, can be introduced very easily by milling slots in the in one of the upper waveguides in something that looks like this. And once you put those slots in, you can actually create this transformation to get this gradient mu. And if you do that, here's the original untransformed lens, compressed Rotman lens, and a control lens, which is just compressed but without that patterning. And what you see is this is the structure that was made. And what you can see, well, barely see, it's too hard to see. My colors are bad. But the uncompressed and the compressed lens give identical performance in terms of steering. The control is off significantly and has worse figures. So this coordinate transformation actually preserves all aspects of this device, yet lowers the profile and is very achievable and results in a structure with no insertion loss and something that has all the other metrics that you'd like. So I'm going to stop there. This would naturally lead into some of the work that is being done now at Intellectual Ventures and Chimeta. Again, I haven't even touched on some of the optics and plasmonics, all of which are kind of related to metamaterials, at least in our group. Just to say that there's a lot here, and that Washington and the Seattle area, I think, is going to have a big impact on this field with a lot of the entrepreneurial thought that's being taken towards metamaterials. So again, thanks for the invitation, and I'll stop there.
We've got time for a couple of questions for Professor Smith.
You have identified that to use these metamaterials in optical frequencies, you need to have thin materials to reduce loss. But if the material is too thin, then you will start losing the effect of the material. So is there an optimum thickness?
There must be, and it always is going to depend on what the application is. So these diffractive optics can be pretty thin. There's other tricks you can play. For example, the group at Harvard is rotating the polarization. So they take a single layer of elements. They come in with a wave. They get an effect in the orthogonal polarization, and they can filter out the original polarization. It's a low efficiency optic, but it's, depending on the application, it might be useful for something. We're trying to get something more traditional, and so we have to play around with substrate materials and designs to try to mitigate the losses. You have to get a certain 2 pi phase shift for diffractive optics, which means for us typically 4 to 8 layers, and that's not too thick. And so depending on how useful of the functionality that we're trying to get, that might be an acceptable loss in some cases. But it's always going to depend on the materials, the design, and the application that you're shooting for.
Other questions?
So in the negative press on negative indexes of refraction, I noticed the term perfect lens come up a couple of times, and I was wondering if you could expand on what they thought that meant, because when you show all these diagrams, you see all this nicely physical stuff that feels like, well, I can imagine loss, and I can imagine narrow-bandedness being, drawbacks of this. When they say the words perfect lens, that's evocative of a lot more sort of mystical thinking, and I want to know if you have an idea of what they mean by a perfect lens.
Oh, yeah. So that was the big controversy. The field was really instigated in large part by a paper that Sir John Pendry wrote called Negative Refraction Makes a Perfect Lens. And what he noticed was any source has both propagating components as well as evanescent components, those that die away. And so he decided to Vestilago came up with the notion that if you had a negative index slab of n equals -1, that if you put a source next to it, the rays go out, but then they come back, refocus, and then when they hit the other edge, they refocus again, so a flat lens focuses. John Pendry said, what happens to the evanescent components of a source? And he found that things just balance in such a way that your decaying exponential component actually grows in the lens and then decays back at the object. So you actually pick up all the near-field components. So he said negative refraction makes a perfect lens in the sense that you could pick up all of the every feature and beat the diffraction limit. Now, what was obvious from the paper and what he understood is that it's a near-field effect and that it would be impaired by losses. But somehow people, I guess, got excited by the headline and then were very disappointed when they found it wasn't going to help them, image the next galaxy or something like that. And so the wave of disappointment that kind of swept over was part of it. And even though he said it in the paper, everyone comes back and says, well, you didn't say it loud enough, right? That was part of what it was. And there's been a lot of cases where people will report things in this field knowing and being clear that there's limitations and that losses will hurt you. But again, the headline gets out there and people get excited, and then when their enthusiasm gets crushed, they get really angry about it for a while.
One last question, please.
Fabricating materials that, suppose you were working in the neighborhood of 5 gigahertz. You mentioned that these little structuring elements, I-beams and resonant loops and so forth, can be anything significantly smaller than a wavelength.
Usually, factors.
Do you run into problems with scale, or is there some trade-off that what gets to be eventually hard about the fabrication?
The fabrication is not the hard part in most cases. If you want effects based on the resonance, trying to get a resonator that, what I didn't say is that most of them are between lambda over 5 and lambda over 10 in size. That's kind of where things work out to get the effects that you want. Fabricating that is not a problem at really any wavelength, including to the nano. The real issue is losses. These are resonant structures. If you want the advanced, kind of crazy, interesting effects, the ones that we all get excited about, they usually require like a negative epsilon or mu, or maybe one between 0 and 1. So that means you have to work close to a resonance. And once you're close to a resonance, losses come in. And so that's even bad at microwave frequencies, where people are very concerned about insertion loss and efficiency. So that is really the toughest part of the engineering, is to try to dance with the resonance, not get too close, but get the benefit of it. And that's usually the design process.
Let's thank the speaker once more for a very interesting talk.